Hello, welcome to a new lecture of Math-S401 Dynamic Optimization. Today we're going to use all mathematical insights and definitions and results that we have seen during the past several lectures, and we're going to use them to analyze the model that we're interested in, which is the infinite horizon dynamic optimization model. And we're going to make the connection between this problem and the Bellman equation, and in particular also the Bellman operator. So let's go to the whiteboard. Okay, so remember our infinite horizon dynamic optimization problem. So we're maximizing a sequence of actions A0, A1, and so on in order to solve the sum from t0 to infinity of beta to the power tf xt at. And then there are a couple of constraints. Well, first of all, the set of actions, the action that you can take should be in g of xt, right? So this gives you the feasible set of actions to take at period t. And then you had a law of motion that said that xt plus 1 is some function r of xt and at, and then x0, the initial state, is given. Okay, so this is our infinite horizon discrete time dynamic optimization problem. And here all the a's are maximized, right? So these are all endogenous, and all the x's will also be endogenous because the a's are endogenous, except for the initial one. All right, so everything here is endogenous except for this parameter. So if we can solve this problem, and you investigate the conditions under which we can solve this problem, then the solution to this problem will only depend on x0. Okay, so we could then write this as a function of x0. Now, in order to find this number, right, or to find v of x0, we can either try to solve this problem, but here we will show that it's actually possible to find this value by solving an auxiliary problem, which is going to be the Bellman equation. Okay, so here this function is going to satisfy the following equation, which is that at any state x, v of x is going to be equal to the maximum of a and g of x of the following function fxa plus beta v r xa. Okay, so rxa is the state tomorrow, right? Given the state x today and a today, this is the state tomorrow. So this is the value starting at the state tomorrow. So here we're maximizing our payoff today plus beta times the payoff of the state starting tomorrow. Okay, so this is the infinite future. So this is our Bellman equation. Okay, and notice here that this is an identity, you can call it, but here we have the v on the left hand side and we have the same function v on the right hand side, right? So in principle, there's no easy way to solve this problem. Okay. However, what we're going to do is we're going to look at what we call the Bellman operator, right? So let's go back to the set c phi of x. So remember, this was the set of all functions v from x to r, okay, that are continuous and bounded in the phi norm. Okay, so what we're going to do, we're going to look at an operator t that's going to go from this vector space to the same vector space, and is going to look very similar to the Bellman equation, except that we don't have v on both sides, but we have tv on one side and v on the other side. fxa plus beta v r xa. Okay, so this is an operator. It takes the function v in the set, and so this should be x, sorry, and gives you for every x a new value, right, tv of x, by solving this problem here. And you have seen that if you can show that t is a contraction mapping, right, if this is a contraction mapping, then iterating this procedure, right, by computing, starting with some v, computing t of v, plugging in t of v here, and recomputing again, and so on, will finally get you to the fixed point, and then this fixed point will satisfy this Bellman equation, okay, because at the fixed point t of v is equal to v. So this will give you the fixed point. So although we cannot solve the Bellman equation, we can basically iterate this maximization problem and get very arbitrarily close to the fixed point for the Bellman equation. And then if you want to solve this infinite horizon maximization problem, we take the function that we have found here, plug in x0, and we get a number that solves our problem. Okay, so that's the general idea of how to solve this infinite horizon problem. So this here, this t is called the Bellman operator. Okay, so what are we going to do today? Today we're going to impose some conditions on the ingredients of this maximization problem, in particular the function f, the coefficient beta, the mapping or the correspondence g, and the function r, and so on, such that this problem is well defined, okay, such that this is indeed a contraction mapping, okay, and then such that this fixed point here that we get here is the same function as this function here. All right, so these are the three things that we're going to establish during this lecture. Okay, so let's write down the conditions. Okay, so we have conditions on x, a, the objective function f, the correspondence g, and then other ingredient is this function r, and then you have beta. Okay, so x and a, we're going to assume that these are subsets of Euclidean space, right? So for example, x is a subset of RL, and a is a subset of RK, okay, and a is a subset of Rm. Okay, and then f is going to be a function from x times a to r, and we're going to assume that this is a continuous function. So we're going to use the theorem, the theorem of the maximum, right? So and we're going to maximize this kind of function, right? So in some sense, we want it to be continuous, right? Because any continuous function to a compact domain will have a maximum, all right? So this is why we impose some kind of continuity conditions on the structure. Then the next ingredient, this is our correspondence G. So remember, G takes an element in X and produces a subset of A. So here we're going to assume that G is continuous. So in particular, it's upper hemi-continuous and lower hemi-continuous. Okay. Again, we're maximizing subject to this kind of constraint, and then upper and lower hemi-continuity will be useful if we want to apply Burgers' maximization theorem. Okay. So next one is R, right? The law of motion. So this takes in state and action and gives a new state. So we're going to assume that also this function is continuous. Okay, and then beta is going to be an element strictly between 0 and 1. Okay, greater or equal to 0, strictly less than 1. So these are, you can say, continuity conditions, and then we're going to impose two more important conditions. So in some sense, we want to maximize this, right? So in order for the sum to be well defined, this has to be bounded, right? This cannot go to infinity, otherwise this value doesn't exist. Okay. So the first kind of condition imposes this kind of bound. So let me state it first. So the maximum over all A, so first of all, for all x, for all possible states, the maximum of A in g of x of the absolute value of fx a Okay, we're going to assume that this is lower or equal to some number m. Okay, there exists in R, such that for all x this is lower than some number, and then times phi of x. Okay, so remember phi of x was a function from a state to strictly positive numbers, r++, and it was continuous. So if this is just the constant function, for example 1, then of course this is equal to 1, and then this basically says that this function here has to be bounded. Okay, but we're not requiring it to be bounded, we're just requiring it to grow not faster than this function phi. Okay, this is basically the idea. And then we have to put a restriction on how the function phi itself can grow. Okay, and then this is imposed by the second condition b. It says that beta times the maximum of a in g of x. Okay, so again this holds for all x and x, of phi of r xa, okay, is less or equal to theta phi x. Okay, so in particular there should exist a theta greater or equal to 0, strictly less than 1. That satisfies this condition. Okay, so here beta is strictly less than 1. Okay, beta is known, this is just simply this beta. So here we're looking at phi of rxa, so rxa should be the state tomorrow when action A is taken. Okay, so this is basically picking the action that's feasible that will give you the highest value of phi tomorrow. Okay, this condition says that if I multiply this by beta, then it should be less than phi of the state today. Okay, so basically this puts a bound on how fast the function phi can grow over time. Okay, so this puts a bound on how fast or how big the objective function can be with respect to phi, and this puts a condition on how fast phi can grow over time. Okay, so we're going to require also these two conditions, and these conditions will be quite important when we derive our results in this lecture. Okay, so let's first look at our first result. You can call it a theorem or a lemma, I don't care. But first, let us look at the Bellman operator, right? So let T be an operator from C phi x. Let T be the following operator, right? Bellman operator, max A in g of x of f xa plus beta vr xa. Okay, and we're going to show several properties of this operator. So first of all, we're going to show that T takes a function v in psi phi x. If I plug in a function here from this set, then it will give me another function from the same set. Okay, so T is an operator. This is basically what it says. And then second, we're going to show that T is a contraction. Mapping. Okay. So basically, now we look at this condition here. Showing indeed that T is well defined, takes a function from this set to this set, and second, that it's a contraction mapping. So for one, well, TV of x is equal to maximum A in G of x of fxa plus beta v r xa. Okay, and assume that v is in C phi of x, so we need to show that TV is also in C phi of x. Okay, that's the main goal here. Well, here we can use Birch's maximization theorem. Okay, so why can we do this? Well, we assume that this is continuous. Okay, we assume that R is also continuous. V of R, so V is in this set, so V is also continuous. So V of R of x and a, this will also be continuous. Okay, so we have a continuous function plus continuous function, which is obviously continuous. So we're maximizing a continuous function subject to an upper and lower hemicontinuous correspondence. Okay, so the value function, so basically this is the value function of this maximization problem. This value function by Burgess' maximization theorem, we know that this will be continuous. Okay, so we already did all the heavy lifting here. T of v will be continuous. So it's a continuous function of x. So the only thing that we need to show is that it's bounded in the phi norm. Okay, TV is bounded in the phi norm. So this is what we're going to show now. So as before, TV of x, well, I can just copy this. I'm going to write the same thing many times today. fxa plus beta v rxa. Okay, and so we're going to want to put an upper bound on this here. Well, first of all, this is the maximization of a sum, and the maximum of over a sum is smaller or equal to the sum of the maxima. Okay, so this will be less or equal to the maximum of a and g of x of f xa plus beta maximum of a and g of x v r xa. Okay, and then of course if I make this the absolute value, well, then it will still be less or equal to. Okay, so I can put this here. Okay, and I know that this here, because of my assumption B or A, I don't remember how I called it. Here, I found it. Here, this condition here, I know that this is less or equal to m times phi of x. Okay, so this is less or equal to big M times phi of x. And then for the second one, let me take the absolute value, right? This is not a problem. So VR xa, and let me divide it by phi of rxa, and then I have to multiply it by phi of rxa. Okay, this will equal to m phi x plus beta. Now here this is less or equal to the phi norm of v, right? Because the phi norm of v is a supremum of this here over all rxa's. Okay, all possible states, this is a state rxa. If I take the supremum over all possible states of this ratio, I get the norm here. Okay, so I can put this in front of the maximization because it doesn't depend on a anymore. So this is the phi norm of v, and then I have the maximum of a and g of x of phi rxa. And now I use my condition B, this one here, right, to show that this is less or equal to m times phi of x plus the phi norm of v, then beta times this is less or equal to theta of phi of x. Okay, so I know that this is less or equal to this. I can divide both sides by phi of x, so tv x divided by phi of x is less or equal to m plus the phi norm of v times theta. Okay, and actually I could have taken the absolute value, right? Then this is the absolute value of the max. And of course, the absolute value of the max is less or equal to the maximum of the absolute values, and then everything goes true. So I could have taken also this. Okay. So this doesn't depend on x anymore, right? This is independent of x. So I can take the supremum over x of this thing here, and the inequality will still hold, right? So this identity, this condition also holds, and this is nothing else than the phi norm of TV, and this is just an upper bound, so I know that this is bounded in the phi norm. Okay, so TV is bounded in the phi norm. So this indeed shows that T is a mapping from this set to this set. Next, let us show that it's also a contraction mapping. In order to show that it's a contraction mapping, I'm going to use Blackwell's theorem. So first of all, for Blackwell's theorem, I need to show that T is monotone, right? So if V is less or equal to W, right? So these are two elements in VW and C phi x. Well, then I need that T of V is less or equal to T of W. Okay, so let's try to do this. So what's TV of x? Well, that's maximum of f xa plus beta v r xa. Okay, and I know that v is element-wise lower or equal to w. So I know that this is less or equal to maximum of a in gx of fxa plus beta w rxa. Okay, so this is element-wise less, so the maximum will be also less or equal. Okay, and then this is nothing else than, by definition, tw of x. So you have seen that tv is indeed less or equal to t of w. Okay, so that was easy for monotonicity. And now for additivity, well, I need to show that t of v plus a psi is less or equal to tv plus theta a psi for some theta between strictly less than 1 and greater or equal to 0. Okay, so that was the additivity. So let's do this. T of v plus a psi at some point x. Okay, so it's written with a lot of brackets here. So what's this? This is maximum of a and g of x of f xa plus beta, right? There should be v here, but we're taking the mapping not of v, but of this function here. Okay, so this is v r xa plus a psi r xa. Okay, so again, we can take this together with this, and then this is the remainder, right? So the maximum of a sum is lower or equal to the sum of the maxima. So this is less or equal to the maximum of a and g of x of f xa plus beta vr xa, and then plus the maximum of a and g of x. I should not have used the same a, right, because I already have an a. So let me make this b, right? So b is here greater or equal than 0. So this becomes b, this becomes b. Now I have here a b, right? In order not to confuse a with a. Psi r xa. And I've forgotten the beta, I think. right? This beta here. Okay. I can put the b in front, it doesn't matter, and now I can use condition b again. All right, this one here. So I have that this is less or equal to the maximum. Oh, maybe I can already shorten it because this is nothing else than TV of x, okay, by definition, plus b, and then this is less or equal to theta times phi of x, okay, which is exactly what we have here, element-wise, and this is in terms of a function, but this is the same statement. So we're done. We have a contraction mapping from c phi x to c phi x, and T is a contraction mapping, right? So we know about the fixed point. There's a unique fixed point. There's a unique v in c phi of x such that tv is equal to v. And of course, this fixed point here will satisfy the Bellman equation. Where's my Bellman equation? Right, here's my Bellman equation. Right, so the fixed point will satisfy this equation here. Okay. Now, so far we have covered the Bellman operator, shown that it's contraction mapping, that it has a fixed point. Now we still have to connect this fixed point to the solution of the infinite horizon optimization problem. So let's go back to this problem. Right, so we chose A0, A1, and so on, an infinite sequence of actions to maximize an infinite sum, beta 2 power t f of xt at, and g of xt, x0 given, and xt plus 1 is equal to r xt at. Okay. So this is a maximization problem over infinite sequence of actions. Okay, and these actions have to satisfy these three conditions. All right, we start at the state x0, then we pick an at in the set, it generates a new state. We pick in a1 in the set, it generates a new state, and a2 in the set generates a new state x2, and so on. Okay, so we start at x0, then we take an a0 in g of x0, and then using this law of motion, right, which is deterministic, we get a new state x1. We take an a1 and g of x1. By the law of motion, we get an x2. We take an a2 and g of x2. We get an x3, and so on. Okay, so this is how the dynamics work. So basically, we have a set of actions, a0, a1, a2, and so on, that have to work in this way. Okay, so let's try to put all of these sequences of possible actions that we can take, right, that satisfy this constraint, into one set. Okay, so we define a path, right, as a sequence of state actions. So let's take the states together with the actions. And x0, a0, x1, a1, x2, a2, and so on, right? So they're infinitely many, such that, well, we start at x0, all right? And for all t equal to 0, 1, and so on, we have that at is in g of xt, right? So this is the first constraint. And then for all t equal to 1, 2, and so on, xt is equal to r of xt minus 1, at minus 1. Okay, so basically a path is defined such that it can be generated by such sequence, the dynamical sequence. Okay, so that pi x0 is the set of all paths that satisfy these conditions, right? Starting at x0. Okay, so this is probably a huge set, right? So the only thing that we require is that AT is feasible given xt, and xt plus 1 or xt is generated by xt minus 1, AT minus 1 via the law of motion. Okay, and basically this is what we're maximizing over, right? We're picking a path from the set in order to maximize this. So we can rewrite our maximization problem as maximize this infinite sum beta to the power t f of xt at subject to, well, x0, a0, x1, a1, and so on, is a path that satisfies these restrictions. Okay, so basically what we have done now, we've done nothing very impressive. We have taken these restrictions, we have taken all sequences that satisfy these restrictions into one set, and then we have just substituted this by this. Okay, so nothing fancy here. So we're going to reduce our notation even further. So let us call a path, I'm going to abbreviate it by, for example, the letter P, right? So P is a path. And let me denote W of P, the value of P, by this infinite sum of xt at. Okay, and here P is a path that is equal to x0, a0, x1, a1, and so on. Okay, so for this path we can plug it in here into this objective function, and normally we hope to get a number out of this, and let me call this number WP. Okay, that's the convention. So now I can write my infinite horizon dynamic optimization problem in a very short way. Basically, I'm looking for the path that's feasible and that maximizes W of P. Okay, so this is now my infinite horizon optimization problem using very short handed notation. Okay, so first thing that we need to show is that this W of P is actually a number, right? Because we're having an infinite sum here. It might be that this is infinite or minus infinite, or even neither of both, right? This sum does not need to converge, right? So the first thing that we need to show is that this number exists. Okay. Then the second thing that we need to show is that this maximum is well defined, right? Because here we're maximizing over a huge set. Can we actually do this, right? Will we find the value that's the biggest one, right? Or will we only be able to get a supremum over the set? Okay, we want actually a path that gets us to the best path. So let me do these things separately. So our first result, okay, so we're starting from a regular problem as before, G R beta. So let this be regular, which means that it satisfies all these conditions, right? So we say that the problem is regular if all these conditions are satisfied. Well, then for all paths that start at x0, WP, this number exists, right? That's the first thing that we need to show. So what is WP? Well, it's the infinite sum of beta to the power t of f xt at, and an infinite sum is nothing else than the limit. So it's the limit for t going to infinity of the finite sum t0 to t of beta to the power t f xt at. So you could say, where does this come from? Well, this is basically the definition of an infinite sum, right? An infinite sum is the limit of a number of finite sums. And this finite sum, let me call this Wt. Okay, so basically we have W1, which depends on the first state and action in the path, or we have W0, right? First state and action in the path, then you have W1, then you have W2, W3, right? So this is for 3 periods, 2 periods, 1 period. And we hope that this converges to some WP, okay? For n going to infinity, or for big T going to infinity. So these are all numbers, right? So these are simply numbers in R. So here we have a sequence of numbers. So these are finite sums. And you hope that this converges to a number, okay? So does the sequence converge? That's basically the question that we try to answer. If the sequence converges, then this is well defined. So it's basically the same question. So how are we going to find out if the sequence is well defined? How do we find out if a sequence of numbers converges? Well, we show that the sequence is Cauchy. Okay, so this is what we're going to do. We're going to show that WT is Cauchy. Okay. All right, let's do this. So let's take the sum up to n terms and the difference with the sum up to m terms. So let n be smaller than n without loss of generality. We have to show that this difference here goes to 0 if n and m go to infinity. Okay, so let's write out what this is. Well, this is the first sum from t0 to n of beta to the power tf xtat minus the sum now from 0 to m beta to the power tf xtat. Okay, so this is sum from 0 to n, this is sum from 0 to m, m is smaller than n, so if I take the difference I get t equal to n plus 1 to m of beta to the power t of f xtat. The absolute value of a sum is less or equal to the sum of the absolute values. Plus 1 to m of beta t absolute value of f xtat. Okay, and now I'm going to use my property A again. All right, so here AT was feasible given xt, right, because it's based on a path P, on a feasible path that starts at x0, right? So this has to be less or equal to the maximum that I can get at xt, and this is less or equal to m times phi of x. So I know that this is less or equal to t equal from n plus 1 to m of beta to the power t times m times phi of xt. So this is equal to m phi xt. Okay, so let's focus on this term here. Okay, and let's try to put an upper bound on this term. Because we want this to go to 0, let's try to put an upper bound on this term. Okay, so we have phi of xt. So what's xt? Well, given how we define the path, xt is equal to r of xt minus 1, at minus 1. Okay, just by definition of the path. Okay, and then we can use condition B here. This one here, just bring beta to the other side. So this should be less or equal to theta over beta of phi xt minus 1. Okay, and we can do the same thing again. We copy the first thing. What's xt minus 1? Well, it's r of xt minus 2, at minus 2. Okay, and then again we can upper bound this by theta over beta of phi xt minus 2. And we can do this again and again and again. All right, so after that many substitutions, here we have theta. How many thetas will we have? Well, t minus 1 we have 1 theta, t minus 2 we have 2 thetas. So at the end we arrive at phi of x0. So theta to the power t, and then divide by beta to the power t. Okay, so this puts us an upper bound on phi of x. So if you use this here, we have that this is less or equal to m t starting from n plus 1. Oh, I'm a bit confused here. N was bigger than m. Okay, so this should be n plus 1 to n, n plus 1 to n, n plus 1 to n, n plus 1 to n. Right, so t should start at n plus 1 to n. Okay, sorry for this. Then beta to the power t of xt, well, we can multiply this by beta to the power t, then this beta to the power t disappears. So we have less or equal to theta to the power t phi of x0. And x0 doesn't depend on t anymore, so I can put it in front. So this is m times phi x0. And then what we are left with is a sequence of theta to the power t's for t n plus 1 to n. Okay, let me continue here. This is less or equal to m phi x0. So this only goes to n, so we can add some terms at the end. Infinitely many, let's say theta to the power t, and I get less than or equal sign. And this is equal to m phi x0, first term, divided by 1 minus theta. And now if n and m go to infinity, what will happen to this? Well, theta is smaller than 1, so this will converge to 0, which means that indeed this distance goes to 0, so indeed we have a Cauchy sequence. Okay. So this is Cauchy, so it has a limit, and you will call this limit w of p, right? So this is the value. So this means if we look at the infinite horizon optimization problem, which we denoted like this, then all these values exist, right? These numbers actually exist, so we can talk about maximizing a set of values. Okay. Okay, so let's continue now. So remember that we had our Bellman operator and our Bellman fixed point. So let V is the fixed point of t. All right, so in particular V of x0 is equal to the max of all a and g of x0 of fxa plus bv r x0a. Right, this is just plugging in x0 into this Bellman equation. Okay, and you would like to solve this maximization problem, so what are we going to do? Well, first we're going to show that for all paths w of p is smaller or equal to v of x0. Okay, that's the first thing that we're going to show. And then the second thing that we're going to show is that there exists a path in p of x0 such that w of p is equal to v of x0. Okay, so this is going to do two things. First of all, it's going to show that this maximization problem, if it exists, is lower or equal to this value here that we can obtain by solving the Bellman equation. And the second one, by showing that there's a path, actually shows that the value is actually attained, right? So if I can show these two things, then indeed this maximization will be equal to V of x0. And this shows two things at once. First of all, it shows that this maximization problem can be solved, right? There's a maximum because here I have the path that solves it. And second, it shows that at this maximum, the value function is equal to the value that I get from the Bellman equation. Okay. So let me show first that for any path w of p is less or equal to v of x0. So v of x0, again, use the definition here, is maximum a and g of x0 plus beta vr x0a. And take any path, right? So for any path, so take any path, let's say x0, a0, x1, a1, and so on. Okay, so here I take the maximum over all a and g of x0, and a0 is one of them, okay, because it's a path. So we know that this is greater or equal to f of x0, a0 plus beta v r x0, a0. Okay, this is the maximum. This is just taking one possible value. Now r x0, a0, this is nothing else than x1. Okay, so this is equal to f of x0, a0 plus beta v x1. And now I can use a Bellman equation, not for x0, but now for x1. Okay, because it holds for every x. Okay, so this is equal to f of x0, a0 plus beta maximum over all a and g of x1 of f x1 a plus beta v r x1 a. Okay, take the maximum over all a's that are here, and a1 is one of them, right? Because this is a path, it should be feasible. So again, I can use the inequality x0, a0 plus beta, plug in a1 in here now, f x1, a1 plus beta times beta is beta squared v r x1, a1 is x2. Okay. Again, I can substitute the v here with this maximization problem, and so on, and so on, and so on, and so on. Okay, so I can do this t times, and then at the end I will get sum from t0 to t of beta to the power t of f xt at. Okay. Plus at the end I have a beta t plus 1 v x t plus 1. Okay, so v of x0 is greater or equal to this thing here. So if you look good, this is a sum from 0 to t. So if I take the limit t going to infinity, right, this here will converge to w of p, right? So v of x0 is greater or equal to w of p, which is actually what we wanted to show, except that now we're stuck here with the remainder, and the remainder will be limit for t going to infinity of beta. This is t plus 1, but if I take the limit to infinity, t plus 1 or t, they both go to infinity. So I have beta to the power big T of v of xt. Okay, so now I have shown that v of x0 is greater or equal to w of p, what I wanted to show, plus some remaining term, right? So I would like this to be equal to 0, right? If this is equal to 0, then I'm done because I have shown this inequality. So let me show indeed that this term goes to 0. So beta to the power t of v of x t. All right. So let's first focus on this one. I know that this is less or equal to the absolute value of v of x t. And now I'm going to divide and multiply over and over again. All right, so divide by phi xt, multiply by phi xt minus 1. No, multiply by phi xt because this is 1. Then divide by phi xt minus 1, multiply by phi xt minus 1, divide by phi xt minus 2, multiply by phi xt minus 2, divide by phi xt minus 2, and so on. At the end, this should be minus 3. At the end, I get phi x1 divided by phi x0, and then I multiply by phi x0. Okay, so these are always the same elements here. Okay. Now let us look at one of these terms, phi x t, and then the one below is phi x t minus 1. Okay. So this is equal to phi of r xt minus 1 at minus 1, and then phi x t minus 1. Then if we use this condition v again, I immediately have that this is smaller or equal to theta over beta. Okay, so if I look at here, then I know that this is less or equal to the absolute value of v xt divided by phi xt, and then theta over beta, theta over beta, theta over beta, theta over beta, and so on. How many do I have? Well, I think t minus 1. It could also be t, okay, but it doesn't matter. It's fine as long as it goes to infinity. I'm happy. Okay, and then phi x0 at the end. Now this here, this is less or equal to the phi norm of v, because this phi norm is a supremum and this is just 1. Then I have theta over beta to the power t minus 1, and then phi of x0. So remember where we were. Yes, we wanted to get a bound on this limit. Right. So beta to the power t v xt. So we have that this is less or equal to phi norm beta to the power t divided by beta to the power t minus 1. So this will give me 1 beta, and then theta to the power t minus 1, then times phi x 0. So if we'll take the limit t going to infinity, here I have also take the limit t to infinity, so t is only here, theta is smaller than 1, so this will go to 0. So indeed here this limit is equal to 0. Okay, so this shows that indeed the value of the Bellman equation at x0 is greater or equal to w of p, right, for every possible path, right? So it's an upper bound. Second thing that we need to show is that there actually exists a path that implements this upper bound, and it's going to be quite easy. So the idea is to look at following problem. So we start at x0. We're going to maximize f of x0a plus beta v of rx0a. Okay, and we're going to call this, there will be a solution to this problem, right? Because everything here is continuous, upper Hemic continuous and lower Hemic continuous correspondence and so on. So one of the solutions, we're going to pick just one of them and we're going to call it A1. Okay. Now A1 we're going to call it A0, right? A0 together with x0 is going to give us x1, and then we're going to again solve this Bellman optimization problem. You can call it f x1a plus beta v rx1a. Pick one solution and we call this A1. Okay, and we're going to go do this over and over again, and this will generate a path, right? And we're going to show that this path, the value of this path, is equal to the value of the Bellman function. So in general, we will have that AT is just a solution of this problem, A and G of xt of fxt at plus beta vr xt at, and then we're going to put xt plus 1 to be equal to r xt at. Okay, and we're going to start at x0. Okay, so this generates a path. Instead of feasible paths, right? And we're going to show that, call this the path p star. I'm going to show that w of p star is equal to v of x0, where v of x0 is the value of the Bellman equation. Okay, and the proof is going to be almost identical to the previous one, except that instead of inequalities, now we will have equalities. Okay, so we start at f vx0. This is equal to this problem, right? And we know that A0 solves this problem, so it's simply equal to f of x0 A0 plus beta v. If I put in x0 here, I get x1, right, as defined here. And I'm going to substitute out again v as maximum of a and g of x1 fx1a plus beta vr x1a. Okay, I know that a1 solves this problem, so this is equal to f of x0 a0 plus beta fx1 a1 plus beta squared v x2, and so on and so on. Okay, so in the end what I will get is t0 to some big number t, beta to the power t, f of xt at, right? This is here over the path that's generated by this Bellman optimization, plus beta t plus 1 vx t plus 1. And then if I take the limit to infinity, it would be equal to this wp star. If I take the limit to infinity, well, analogous to what I have shown previously, I can show that this goes to 0. Okay, so this is a fixed number. It's equal, I can take the limits, right? So v of x0 is equal to wp star. Right, so not only is the Bellman value of the Bellman function an upper bound of the infinite horizon problem, it's actually equal to the upper bound, and I can generate a path that generates this value, right? And how do I do this? Well, basically I'm just solving the Bellman equation over and over and over again. Okay, good. Let's take a break and then come back with an example. So the example will be quite easy, and it will be, I'm not a macroeconomist, but I think this is known in macroeconomics as the AK model. So it's a very simple, simple, it's an intertemporal horizon optimization problem in an economy with a representative consumer and a very easy production function. So how does the problem look like? So we're going to maximize by choosing consumption amounts, C0, C1, and so on. And we're going to maximize utility, right? So the sum from T0 to infinity of beta to the power T of the utility of Ct. And we're going to have some constraints. And the constraint is going to be that, so there's capital accumulation. So the capital in period T plus 1 is going to be equal to A times the capital at period T minus how much of this output you're going to consume, Ct. Okay. And then you have that KT/Ct is greater or equal to 0. Okay. And K0 is given. You have to start from somewhere. Okay. So this is called the AK model because it's, I think this has to do with the production function is A times K, right? So here A is a parameter and it's greater or equal to 0. Okay. So let's look at the different ingredients, right? So here are, in our objective function, the function f is given by u. Okay, and it doesn't depend on the state k, but it depends on the action c. Okay, this is a special case. So we assume that u goes from r plus to r plus. Okay, so the utility is non-negative. Normally, if it's become negative, normally if it's bounded from below, we can renormalize, right? Just by adding a fixed number to the utility. And then by renormalization, we can impose that u of 0 is equal to 0. Okay, so the utility function looks like this. It starts at 0 and it's non-negative. And we're going to assume that it's increasing. Okay, so it goes up. The more you get, the more utility you have, and that it's concave. Okay, so it looks something like this. Okay, so these are the assumptions that we're going to impose. And then the second ingredient is our correspondence G, right? So G takes a state. So here it's capital, right? So capital is an R plus. And it gives you a subset of consumption bundles that consumption amounts that you can consume, so it goes to R plus. Okay, so if K is the state, then G of K, how much can I consume? Well, 0 is the lowest amount that I consume, and what's the highest amount that I consume is AK, right? So G of K is the closed interval 0 AK. So if I draw it here, so if this is K, G of K should be straight line, right, with slope A. So this is how the correspondence looks like. Okay. And then I need the law of motion. So it takes an amount of capital, and it takes an amount of consumption, and it produces a new amount of capital, and it's given by kt plus 1 is r kt ct, right? And here r is equal to a times kt minus ct. Okay, so this is my function r. Okay, so I think I have all the ingredients. Well, the starting value is equal to k0. Okay. So I would like to know when I can solve this problem. When is this problem well defined such that it has a good function v of k0, and well, I have to check if all these properties are satisfied, then I'm happy. Okay, so first of all, f should be continuous. Okay, so I should add here that u is continuous. Okay, property that I forgot. G is upper hemicontinuous and lower hemicontinuous, so this is G. Well, you can easily verify that both upper and lower hemicontinuity are satisfied for this correspondence. Okay, so that's not a problem. And then R is continuous. Well, yes, this is a continuous function of KT and CT. Okay, so no problem here. Then you had the beta. Well, beta is simply this beta here. So we require this to be strictly lower than 1 and greater or equal to 0. And then you have these two conditions kicking in. Okay, so let me write explicitly what these conditions are, so we can talk about them. So condition A requires that max of the action that you can take, so here this is consumption, in g of x, so this is 0 k. Okay, so these are the feasible amounts of c, of the absolute value of uc is less or equal to m times phi of k. Okay, I haven't defined phi yet, so basically I have to find the function phi that satisfies this. Okay, and then b is the maximum, is beta times the maximum of c in 0 ak of phi of rkc, right? So what's rkc? Well, this ak minus c. Okay, this should be lower or equal to theta, for some theta strictly lower than 1 of phi k. Okay, and I have to find the function phi k that satisfies this condition. So what function to take? Well, that's the question, and that's a bit of a feeling maybe that you need to acquire. So normally it's not a bad idea to somehow mimic with phi this function here. Okay, so for example, we could define phi k to be equal to u of k. It's continuous, so that's good. There's a small problem that this is not strictly positive. Okay, so we can make it strictly positive by, for example, adding 1, or we can make it strictly positive by taking the maximum of some number, let's say 1 and uk. Okay, so if I would draw this, this was my utility function, and this is here 1. Okay, so my phi is here this, and then it goes like this. Okay, so this is my phi function as strictly positive, so that's not a problem. Okay, and I have to show that this satisfies both this and this condition. Okay, so as it will turn out, whether these conditions are satisfied crucially depends on the parameter a that we said is non-negative, but we haven't said anything else. So let's first take the case where a is smaller or equal to 1. Okay, because this is the easier one. So let's go to condition A. So max c in 0 ak of absolute value of u of c. So the absolute value of doesn't matter because u is non-negative. Okay, and u is increasing as we assumed, so the maximum will be reached when c is as high as possible. Okay, so this is u of ak, and here a is smaller or equal to 1, and this is which means that a of k is smaller or equal to k, so this is less or equal to u of k. All right, and u of k is smaller or equal to the maximum of 1 and u of k, and this is equal to phi of k. Okay, so this condition is satisfied here with m equal to 1. Okay, no problem. And now let's go for b. you have beta times the maximum of c between 0 and ak, and now we need the function phi, right? So this is the maximum of 1, and phi is an ak minus c, right? So this should be u of ak minus c. Okay, so here I have a maximum of a function that's a maximum of two things. Okay. So c only enters here in negative way, u is monotone, so the best thing that I can do here is to put c equal to 0. Okay, because then ak minus c will be maximum, and then this value will also be maximum. So this is equal to beta times the maximum of 1 of u ak. This is very close to my original function psi, except that here I have an a again. I want to get rid of the a, but I can use again monotonicity here, right? So this is less or equal to beta times max of 1 of u k. So this is equal to beta times phi k. And here beta is of course strictly smaller than 1, so I can put theta equal to beta in this case, so the condition b is also satisfied. Okay, so this is for the case where a is smaller or equal to 1. Now let's try the case where a is strictly bigger than 1. Okay, and we're going to use or try to use the same procedure. So for the first condition, again we have that max c between 0 and ak of absolute value of uc, or uc, they're not negative, will be equal to u of ak. Okay, so now we somehow want to get rid of the a, right, because this is closer to psi, and now we can use concavity of the function u. Okay, because a is bigger than 1, we have that 1 over a is smaller than 1. Okay, so if you take the convex combination 1 minus 1 over a of u0 plus 1 over a of u of ak, okay, because of concavity, this is less or equal to u of the convex combination 1 minus a of 0, which is 0, plus 1 over a times ak, which is k, so this will be less or equal to u of k. Okay, so this follows by concavity of u. And of course, by assumption, this is equal to 0. So if we rewrite this, we get that u of ak is less or equal to a of u of k. Okay, so let's use this here. You have that this is less or equal to a of u of k. And of course, this is less or equal to a of max 1 uk, and this is equal to a of psi k. So now here we have that this condition satisfied for m equal to a. Okay, so concavity saved our life here. Let's see if concavity can do the same thing again. So for the second condition, I needed that b times maximum of c between 0 and ak of maximum of 1 and u ak minus c. This was the left hand side. Okay, again, optimal value of c is equal to 0, so this is beta times maximum of 1 and u ak. Let's try the same trick again. So this is less or equal to beta times the maximum of 1 and a uk, and a is bigger than 1, right? So this is less or equal also to the maximum of a and a uk. I can put a in front, so this is equal to a times b beta times the maximum of 1 and uk is equal to a times beta times phi of k. Okay, so here I have this kind of condition where theta is equal to a times beta. However, theta has to be smaller than 1. So this requires that a times beta is smaller than 1. Okay, so a is strictly bigger than 1, but it's still possible that a times beta is strictly smaller than 1. All right, so it will depend on the value of beta. If beta is small enough, then this condition will be satisfied. If beta is too large, or a is too large, then this condition will not be satisfied. Okay, so it depends on the value of beta with respect to the value of a. So here this was a condition for concavity, but for some utility functions, it's even easier to get a better approximation, right? So for example, if I have utility function uc, which is equal to c to the alpha or something, right? So here alpha is smaller than 1 to have a concave function. Well, then u of ac is equal to ac, u of ak, sorry, is equal to k alpha. This is equal to a alpha k alpha, right? So basically here we get the inequality or equality that u of ak is equal to a alpha uk. Okay, so we get the parameter alpha in addition here. So then the first condition, derivation of the first condition is exactly this analogous, but for the second one we get an easier bound in the sense that beta max 1 uak is smaller than beta a to the power alpha of phi k. Okay, so in this case you only require that beta a to the power alpha is smaller than 1, and because alpha is smaller than 1, okay, this will be less strong than this requirement. Okay, so basically you have a trade-off between the discount rate, right, has to be small enough, or a has to be small enough, or the utility function has to be sufficiently concave, right? If one of these conditions are sufficiently guaranteed, so this thing here is smaller than 1, then all our conditions are satisfied. Okay, so you can actually have a production function ak where a is bigger than 1, right? So you make more than proportional output from a given level of capital, but then this has to be satisfied. Okay, so this was today's lecture. Thank you for watching.